Welcome to Winning Edge. Today we will discuss surface chemistry. Surface chemistry is basically understanding how different chemical species will interact with each other on molecular level. It has widespread applications, right from development of new products, research, or mass-scale industrial productions. We are using many applications of surface chemistry without even knowing it. The simplest examples is our bike's exhaust. Without this bike exhaust system, the contamination level or the exhaust gases that will come out of the engine will be very polluting. That is the reason this catalytic converter device was installed. And this converter device, using precious metals like platinum for conversion of unburned hydrocarbons, CO, into acceptable gases. But as we know, these precious metals are very costly. So to use these precious metals in these catalytic converters is a daunting task, because then we have to cover a very huge area with platinum. If we do so, the cost will go up tremendously high. That's where surface chemistry comes to picture. We are using in our catalytic converters atomic levels of depositions of platinum over the huge surfaces for converting our unburnt hydrocarbons and CO and other noxious gases to acceptable level of gases. This is just one application we have discussed. Nanotechnology, which is going or developing day by day and having a huge application in bioindustry, biomedical industry. Now let's talk about basics of surface chemistry. Adsorption. Adsorption means accumulation of molecular species at the surface rather than in the bulk of solid or liquid. Here we see, for example, CO, this carbon monoxide, when it just stick to the surface of this solid, it's called adsorbed or adsorption of CO on surface. It doesn't go in the bulk of it, it stays on the surface only. So this is the definition of adsorption. Absorption is the second definition, which means substance is uniformly distributed throughout the bulk of solid or liquid. For example, sponge, if you put it in water, it is completely soaked, which means water gets absorbed into sponge. For understanding adsorption, we have to understand interaction between adsorbate and adsorbent. These interactions can be two types, like physiosorption, which means adsorption is having only physical interactions, and chemisorption, which means adsorbent and adsorbate having chemical interactions. Let's try to understand first physiosorption. In physical adsorption of gas on the surface of a solid, adsorbed on account of weak van der Waals forces. That's the first point. In physiosorption, the interaction is based on van der Waals forces. As the van der Waals forces are universal, physical adsorbent surface lacks specificity. So adsorbent means the material that provides a surface for adsorption, and adsorbate means the substance that is going to be adsorbed. Second point, we know it lacks specificity. Easily liquefiable gases like with a higher critical temperature are readily adsorbed as the van der Waals forces are stronger for these gases. We can understand this from order of adsorption like sulfur dioxide, methane and nitrogen. So order of adsorption is sulfur dioxide, which is having higher critical temperature, is higher than methane. In turn, methane having a higher adsorption than nitrogen. Physical adsorption for gases follow Le Chatelier's principle. This physical adsorption rises sharply with rise in active sites. Sites of adsorption for the gas molecule increases with increase in the surface area of adsorbent. So we can understand adsorption sites are required for the physical adsorption, and increasing the surface area in a solid means increasing the number of sites for adsorption. In turn, with increase in surface area, we can see higher adsorption is possible. Enthalpy of adsorption is fairly low compared to chemical adsorption. Here, physical adsorption, this enthalpy of adsorption is only 20 to 40 kilojoule per mole. Chemisorption. In chemical adsorption, gas molecules are held to the solid surface by chemical bonds against weak van der Waals forces in physiosorption. Chemisorption is highly specific and it will occur only if there is a possibility of chemical bonding between adsorbent and adsorbate. Transition metals due to higher hydride and aluminum oxides are the examples of chemisorption. Chemisorption involves compound formation. It is usually irreversible in nature, unlike physiosorption, which is reversible in nature. Third point, it doesn't follow Le Chatelier principle like our physiosorption. It increases with increase in surface area. It is same like physiosorption and depends upon the number of sites available per unit area. Enthalpy of chemisorption is very high compared to physiosorption. Next topic is catalysis. Substance which alter the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalyst. The phenomena is known as catalysis. Acceleration of rate of reaction using a substance that do not react chemically or undergo any quantitative change is known as catalysis. Here is an example. This is the activation energy and this is the extent of reaction. From here we are starting energy level, reactants only. Reaction proceeds, go over and reach to the product stage. Then we get catalyzed reaction. Here we see it follows an alternative path which having this activation energy low, thus passing through it and giving the same product. The net energy difference between reactant and products is same for both uncatalyzed and catalyzed reaction. Only difference is activation energy path. Here we see, like you see here, these metal atoms, they adsorb hydrogen and then provide a medium for oxygen to react with the hydrogen atoms to give us water. Promoter are substances that enhance the activity of a catalyst, while poisons decrease the activity of catalyst. Homogeneous catalysis and heterogeneous catalysis. Catalytic reactions can be of two kinds: homogeneous catalysis as well as heterogeneous catalysis. Let's have a look at it one by one. First, homogeneous catalysis. When the reactant and the catalyst are present in reaction in the same phase, liquid or gas, the process is called homogeneous catalysis. Like oxidation of sulfur dioxide to sulfur trioxide in the presence of nitric oxide vapors. This is a nitrogen dioxide and oxygen. Nitric oxide molecules act as a catalyst, facilitate the reaction to go for sulfur trioxide formation. Because all the constituent reactant and catalyst are present in the same phase, we call this reaction homogeneous.